Welcome back to the discussion on chi-square. I'm not going to be going over the binomial and Poisson distributions in terms of the math behind them, but I would like to go over the math between the chi-square goodness of fit and the chi-square test of independence or test of association, whichever one that particular textbook or list likes to use. So as a reminder, the chi-square goodness of fit is for one categorical variable, and it can be dichotomous, nominal, ordinal, any of those will be fine. And then the chi-square test of independence, where we're looking at the relationship or association between two categorical variables. And so this kind of summarizes a lot of different possible combinations. So in terms of the chi-square goodness of fit, remember the two things that we need to know about specifically are we need to know the observed number for each of the categories, and we also need to know the expected number for each category. So the first thing that I'd like to show you is how we calculate that expected value. So here we have our example. We have smokers and we have non-smokers, and we have drawn this sample of 80 individuals. And our first inclination is to just look at how many were in each category. But what I want to do is first have you look at the expected numbers. Let's say that we're running this statistical test and saying we expect 25% to be smokers and 75% to be non-smokers, and those two need to be obviously they need to add up to include all possible choices. So here we have our expected. Literally the way you calculate expected is you take 25% of 80, which is 20. And so this is not more complicated than it looks. If you guessed that the expected number was 20, you were absolutely correct. And then what that means is the other 60, because the total is 80, 75% of 80 is 60, and so that's our expected count. Now, here's where it actually gets a little bit interesting. When we say we expect 20 smokers, let's say in our sample we actually get 20 and 60. That's not very likely to happen, but we would say, yes, that's kind of obvious. It looks like, let's go back to the way this is worded. How well does a sample fit a specified proportion for each of those categories? And I would say, in that particular case, it fits it really well. It fits it exactly the way we would have expected. But then here's the catch. What if we only had, say, 19 smokers and we had 61 non-smokers? Would you say that's extremely different? That totally surprises me. It really is a shock. I can't believe that we got 19. That's really outside of what I would expect at all. And I think most people would say no. 19, 20, it's kind of close. I'm not expecting to get exactly 20. It'd be kind of interesting if I did, but 19, that's not like out of what I would expect to be sort of ordinary. Now, what if instead of 19, I said, okay, well, what about, oops, guess I can't go back quite that far. What if it was only 18 and 62? Or 17 and 63, or 15. What if it was 15? 15 versus 20. Is that different enough that I would say, seems like there's something going on here? So that's the kind of thing that, I guess I can't just back up. It kind of takes me back to the beginning. I would say that for most people, if I put in here there were 5 smokers and 70, I can't add apparently, 75 non-smokers, most people would say, that's pretty different. That's really outside of what I would expect just by sort of randomness. So we kind of have a hunch about these kinds of things. However, In statistics, we want to use math and kind of the probabilities of things to answer those questions, not just our own personal hunch. At what point does our number become different enough from our expected value that we'd say, that it seems like our sample might actually have come from a population that's different than what we're testing. So that's exactly what the chi-square does. And I'll show you here how that is calculated. You'll notice that I've used this symbol. It's kind of like a fancy X, and it's the Greek letter chi, C-H-I, and so that's why we call this a chi-square, because we take chi and square it. Literally, it's not any more difficult than that. And so the way that is calculated is that we add up, and this symbol right here means the sum of, so we add up all of the combinations of observed minus expected squared, and then divide those by expected. So let me show you what that looks like for this example right here. So I'm going to say my chi-square is equal to the observed minus the expected, so 5 minus 20 squared, divided by, and what's the expected here? It's 20. And then remember how I said that I'm summing it? This actually has more notation. It has little i's and kind of all sorts of things, but I didn't want to complicate it. I basically just wanted to show you that we're adding them up. Then I need to take the difference here between the observed minus expected for all of my possible categories. So I'm going to say 75 minus 60 squared divided by expected. See how it's my expected? So 60. So essentially I have 15 squared over 20 plus 15 squared over 60. And the important part of the squaring is that one thing that you'll notice is sometimes the observed value is less, and sometimes the observed value is more than the expected value was. And so what that does is by squaring it, we get rid of the negative and the positive, so that when we add them all together, we're really adding up the absolute value of some of those, the magnitude of those differences, rather than having them play against each other. And when you think about it, we will unless the numbers were exactly what the expected were, we will have some are pluses and some are minuses. And so this difference between observed and expected happens to be a positive number, and 15 minus 20 happens to be a negative number. So we don't want those to cancel each other out or even partially cancel each other out when we calculate the chi-square. We want it to be the magnitude. And then remember that this is kind of a family of distributions, and so you would need to either run it on a computer, and it would know how many degrees of freedom you have, and it would tell you, is that finding something that's way out here, kind of in the tail, like less than 5% chance of that happening sort of randomly, just on its own, or is that something that's kind of more in this region right here? We expect it to be a little bit different than 20, maybe 19 versus 20, that kind of thing. And so where does that fall along that probability? So So essentially, just like we learned with the t-distribution, any chi-square that you calculate is then converted to whatever the p-value is that goes with that, and that's what we're showing right here, is if it's less than or greater than the p-value that you've decided as your cutoff. Okay, so that is the one sample. Sorry, not one sample. That's the chi-square goodness of fit. And sometimes you'll see me actually write that kind of chi-square goodness of fit, GOF. So if you see that anywhere, that's a pretty common abbreviation for chi-square goodness of fit. So that's taking one variable and looking to see if it's distributed appropriately, like the percentage-wise, in each of the different categories. The other kind of chi-square, the chi-square test of independence or association, depending on how you look at that, has to do with taking two variables. Now what I've done here is I've kept this same variable smoker and non-smoker, and at the end I'll tell you why it wouldn't always be set up this way, but just for ease of comparison, what I've done is I've made that so that you can look at those two examples and compare them. So don't get too hung up on causation and all of that for this particular example. What we're looking at here with the chi-square test of independence, come on over, is whether two categorical variables are dependent on one another. Another way of saying that is I want to test whether men and women are equally likely to be smokers, or test whether the proportion of men and women who are smokers is the same. So see how we're using things that show that they're independent from each other, they're the same, they have the same percentage or proportion, regardless of which gender a person is. So the first thing again that I want to do is I want to calculate the expected values for each of these cells, and I want to do that because I think once we get the actual values in there it can be a little distracting. So let's for now just say that we know based on our sample that we have 50 smokers and we have 150 non-smokers, and also we know that we have 100 men and 100 women. And so we want to know if smoking and gender are associated. We want to know if I know something about a person's gender, do I know more about whether they're more likely or less likely to be a smoker or a non-smoker. And so the important thing is these numbers here, the 100 and 100, have to add up to the total, and these two numbers also have to add up to that total. So we have satisfied that. We don't have any missing cells, and so that's taken care of. So the next thing is we want to calculate the expected values, and I'd like to show you how to do that. So here we have 100 individuals, and we want to know how many of them we would expect to be male smokers. Now, probably conceptually the easiest way to think about that is to think about the proportion that are smokers. So we have 50 out of 200 that are smokers, and that is 25%. Now it wouldn't have to match the one that I had up here as the example. I just happened to have it match just so that it wouldn't be confusing, but it wouldn't necessarily. So in other words, 50 out of 200 are smokers, and so if I have 100 people in this particular column, I would expect 25% of them, or 25 of the 100 is my expected. So and you could do the math for all the rest of them. Since these two groups are even, this number 25 is also the expected for that particular cell, and you can either take 150 out of 200, which is 75%, and then multiply that 75 times the 100 individuals and say 75 would be the expected here and 75 would be the expected here. Or you can just do the math and subtract 100 minus 25 is 75. So any way that you do that, you should come up with the exact same answer. So what I just showed you is how do you calculate the expected value when it's a really easy and obvious calculation. I set this up in such a way that you could just calculate the percentage out of 100 and it was an easy number to come up with. But let me give you a general equation, and I want to also show you why it works. The expected value is equal to, and I'll put T column times T row divided by T total. So T column is the column total And so basically in this particular case, let me find another color. That would be, if I'm calculating this cell right here, the column, or right here, the column total is 100. So that would equal 100. The row total for that particular row is 50. So times 50 divided by the total, and that's this number down here in the bottom right corner, so 200. So 100 times 50 divided by 200 should equal 25. So go ahead and pull your calculators out and you can see exactly how that works. When we did it kind of the intuitive method, we took the column total, which was the 100. It's the same as saying 100 times 50 over 200. So that's the 25% right there. So column total times row total divided by total will get you your expected value for any given cell, and it has to be the column total for that cell and the row total for that cell. So that's the equation to calculate the expected value if you don't have easy numbers like we have set up in this particular example. So that's calculating the expected for, now you know how to calculate expected for both chi-square goodness of fit and chi-square test of independence. Now, in terms of calculating the chi-square for this particular example, we would need to know what the observed is for each of these combinations. So male smoker, female smoker, male non-smoker, female non-smoker. And what I'd like to do that's a preliminary to what I call the degrees of freedom calculation is that I want to show you that if you add a number to any one of these cells, then all the other cells kind of come automatically to how what the value is for that one. So let's say in this particular example, I have my 4 groups. Let's say that just for the sake of argument, that of these 50 smokers, 49 of them are male. Now, as soon as I fill in that one cell, I want you to notice what happens. All of the other cells are predetermined because I've already selected one. So what I mean by that is, since I know that this is a total of 50 and this number here, the observed number is 49, this has to be 1. In order for the male smokers and the female smokers to add up to 50, it has to be 49 plus 1. So I couldn't choose this one. It was sort of already decided. Similarly, this row down here is going to be 51 because I know my total for that column is 100, so 49 plus 51 is equal to 100. And then my last cell, you could get that any number of ways. Let's say we have the number there is 99. Because this column total has to be 100, or because this row total has to be 150, or because the total needs to be 200. So I can only fill in one cell before the other ones are already determined to be something. So let's go ahead and use those numbers and calculate the chi-square. Remember, it's the sum of all of these observed minus expected, and we have 4 cells, so we're going to have 4 of these equations. So let's go ahead and put those in here. I know that for the top left cell, male smokers, my observed is 49 minus 25 squared divided by 25 plus, then I have my top right square. I have 1 minus 25 squared divided by 25. My bottom left cell will be 51 minus 75 squared divided by 75. I have to move over a little tiny bit. Plus 99 minus 75 squared divided by 75. So we could do all of that calculation. We would come up with a chi-square number, And then on this distribution, that would fall in a specific location. Wherever it is, whether it's way far out here beyond our level of what we call kind of like our cutoff for that particular research question, we would either reject or fail to reject the null, that there is no relationship between smoking and gender. So that's how chi-square is calculated. You could probably guess that this one's going to be pretty significant because those numbers are kind of large. So the last thing that I want to talk about in this particular video is the whole idea of degrees of freedom. And the way that I teach this is that if we think about, let's go ahead and look at some examples that have to do with this kind of 2x2 table. Here we have, and I'll just draw another one. Here's a 2x2 table. And in a way, it doesn't matter which are the rows and which are the columns, but I will give you a hint, and I sort of alluded to this earlier. Usually, if you have some kind of a causal sort of a relationship, usually the exposure is here on the left-hand side, yes, no, and the outcome is here as the columns. So this would be a yes, no. And in this case up here, we actually did it backwards of what I would normally recommend for that. There's no hard and fast rule, and I hope you realize that it totally does not change the value of the chi-square if you trade the rows and the columns, if you switch them, as we kind of did here in this particular example with smoking and gender. So we would probably be more likely to say gender is a predictor of whether somebody becomes a smoker, if it's this obvious that males are more likely to be smokers. So there's no hard and fast rule. I generally try to put my exposure here just because that's where people are used to seeing it. So if they're looking for it there, then it might throw them off if I trade those rows and columns. However, if I have a specific variable that has a whole bunch of columns and only 2 rows, then I would be pretty likely to trade them just so that it would fit on the page better. So there's nothing really obvious about that kind of a rule, but if you do have a 2x2 table, I think most people are looking for that the exposure on the left and the outcome at the top. And that kind of goes along with the way we calculated odds ratios and relative risks too, so it's consistent between epi and biostat. Okay, so back to the whole idea of degrees of freedom. This is how I like to think about it. If I have something that is a 2x2 table, what the official calculation for degrees of freedom, so df, is equal to the number of rows minus 1 times the number of columns minus 1. And the easy way to do that, if you just want to cover up one of the rows, and I'll shade it in here because you can't see me covering it up on my iPad, and then I scribble out, I also cover up or scribble out one of the columns, you'll notice all I have left is 1 cell. So that's my 1 degree of freedom. So you can think of it in terms of an equation, or you can think of it in terms of rows and columns in the table. Let's do a couple more of those just so that you can see how that works. So here's another one. I'll make it a little bit smaller. There's a 3x2. So I'm going to either cover up or scribble out the rows and the columns, 1 row and 1 column, so that kind of takes care of this idea, the minus 1, minus 1. So we end up with 2 rows minus 1, which is 1, times 3 columns minus 1, which is 2. So 1 times 2 is equal to 2. And here's our 2 degrees of freedom. And so it works out really nicely whether you like to do that visually or whether you think about it more in terms of a mathematical equation. The importance of that, remember when we put this first number into this into this table. What happened is that the other three automatically had to be a certain thing if we knew our marginal totals, these four totals around the outside. So we were not free to put any number we wanted here. We couldn't have put a 4 because then this number would not have been correct, the 50. We are not free to put anything we want there. In this particular case, where we have a 2 by 3 table, we can choose any two cells, actually not quite any two, but we can choose a variety of two combinations of cells because we know our column totals and we know our row totals. And as soon as those two cells are filled in, the other four automatically have to be a specific value. We are not free to choose. We don't have that freedom. So degrees of freedom, that's the freedom part. We are not free to choose any number for that particular cell. So we have to pick a specific number. Let's do one that's a little bit bigger, and I'll even... So let's use these as our dividing point. This is a, let's say we are testing the relationship between education level, and we have 6 categories, like no elementary school, graduated 8th grade, blah, 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 all the way up to, are you a master's or graduate student? And then we have something else that maybe has, let's see, so 6 times 8, that's a lot of possible combinations. It would not be as usual to have that kind of a chi-square, but it is possible. Chi-square works exactly the same way. The math works the same. And so I want to do this both ways. First of all, I'm going to scribble out a row, and I'm going to scribble out a column. And I could take 5 times 7, or I could just number them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. Or 7 times 5 is 35, and so I have 35 degrees of freedom. My chi-square distribution, remember this thing right here, looks different when you have 35 degrees of freedom. It's slightly a different shape. The other way I could do this is I could say df is equal to rows minus 1 times columns minus 1. So rows is 6 minus 1 is 5, and columns is 8 minus 1 is 7, so 5 times 7 is equal to 35. So either way you do it conceptually, to kind of like, I actually physically, I use either a pencil or cover up a row with my finger. If you were given something that's not quite so unwieldy and covered this up, you could see, oh, okay, there's 9 degrees of freedom. A 4 by 4 table has 9 degrees of freedom. So degrees of freedom is something that could show up for you on some kind of like CPH exam kind of a test. Also, the whole idea of what's the equation for certain things. Every once in a while with biostatistics, they'll say, okay, what would be the equation you would use in order to calculate the test statistic? And so if it's a t-value is equal to, and whatever it is that's that t-value. Every once in a while they'll ask you that, just so that they kind of have a sense of whether you understand the math behind it, not just relying on p-values and test statistics. So that concludes my discussion on chi-square goodness of fit and the chi-square test of independence or association. Thank you for joining me.